All right, welcome back. Today, we're putting on our detective hats and diving into a real chemical investigation. We're going to look past what you see on the surface of a chemical equation to find out what's really going on, the secret plot happening behind the scenes.
Sounds a little weird, right? A secret plot? But think about it. Any good story has hidden characters, secret steps, and an ending that, only clicks into place once you know the whole story. Well, guess what? A lot of chemical reactions are just like that. They've got a story to tell, and today, we're going to be the ones to figure it out.
Okay, so every investigation needs a case file, right? Ours starts with a reaction that looks super simple, like almost boringly straightforward on paper. But as you're about to see, looks can be, well, very deceiving. So here it is. You've got hypochlorite reacting with iodide, and boom, you get hypoiodite and chloride. Seems simple enough. Two things go in, two things come out. This balanced equation is kind of like the official story. It tells us the beginning and the end. But it tells us absolutely nothing about the journey, how we actually get from point A to point B. And this, my friends, is where the plot really thickens, because experiments show there's this mysterious character, the hydroxide ion, OH negative, just lurking in the background. It's not a reactant, it's not a product, but it totally changes how fast this thing happens. It's like a secret agent, pulling strings from the shadows. So how is that even possible? Well, to figure that out, we've got to dig deeper. Right, so to crack this case, we can't just look at the start and finish line. We need to expose the entire secret plot, that series of hidden steps that chemists call the reaction mechanism. This is the real story. And here it is. The proposed plot has 3 separate steps. And hey, would you look at that? A couple of new characters just showed up, HOCl and HOI. See how they're made in one step, and then poof, they're used up in the next? They're totally crucial to the whole thing, but they never make it to the final curtain call. These are our secret accomplices. Now, these fleeting characters, our HOCl and HOI, they have a proper name. They're called reaction intermediates. Think of them as the go-betweens, the secret messengers that make the whole operation possible. They pop into existence for just a split second before they're turned into something else. And that's exactly why you never see them in that final overall equation. They're the unsung heroes, or maybe villains, of our chemical plot. Okay, so how do we prove this secret plot is actually what's happening? Well, any good chemical detective needs a couple of special tools. We can't just guess here. We need some solid logic and a couple of really powerful assumptions to break down this mechanism and see if it actually lines up with the evidence. Our 2 big tools are the fast equilibrium assumption and the steady state approximation. The first one, fast equilibrium, is for our first step. That step goes back and forth so fast that it's basically always in balance. The second one, the steady state approximation, is perfect for those super reactive intermediates we just met. It basically says they get used up as fast as they're made, so their concentration never really builds up. It just stays at this constant, super low level. All right, now for the fun part. We get to use these tools to be code breakers. The mission? Translate that 3-step mechanism into one single mathematical equation. We call it a rate law, and this equation will let us predict the reaction speed using only the stuff we can actually measure in the lab. So the objective is crystal clear. We have to get those secret intermediates out of our rate equation. We can start by looking at the last step, the one that makes our final product, OI minus. The rate there is just a constant, K3, times the concentration of HOI and OH minus. But we've got a problem. We can't measure the concentration of HOI. It's an intermediate. It's there and gone in a flash. And that's where our first tool comes into play. We're going to use the steady state approximation on HOI. This lets us make a really powerful assumption. The speed at which HOI is made in step 2 is exactly equal to the speed it's destroyed in step 3. And that gives us a way to solve for its concentration, even though we can't measure it directly. And voila! Once we plug that in and do a little substitution, the math works out beautifully. Our rate law now simplifies down to just the rate of that slow second step. So we've gotten rid of our first secret accomplice, HOI. 1 down, 1 to go. But we're not out of the woods yet. We still have that other intermediate, HOCl, hanging around. Okay, for our second intermediate HOCl, it's time to pull out our other tool. Remember how that first step is in fast equilibrium? Well, that means we can assume the forward reaction and the reverse reaction are happening at the exact same speed. We just set their rates equal to each other, and that lets us solve for the concentration of HOCl using stuff we can measure, like our reactant OCl- and, yep, our mysterious character OH-. So, after all that detective work, plugging one equation into another, getting rid of our secret accomplices, we finally cracked the code. It is time for the big reveal.
And here it is, the final rate law. So what's it telling us? It says the reaction speed depends on the concentration of our reactants, iodide and hypochlorite, but, and this is the key part, it's inversely proportional to the concentration of hydroxide. Our whole theory, our three-step mechanism, has just given us a prediction that we can actually test.
And of course, any good theory has to stand up to the evidence. This right here, this is our forensic evidence. Real data from a real lab experiment. Our rate law, the one we just figured out, has to be able to explain these numbers. This is where the rubber meets the road, where theory meets reality.
Okay, let's look one more time at that final equation. Our mysterious character, OH-, it ended up in the denominator. So what does that actually mean? What is it doing to the reaction?
It means OH is an inhibitor. It's actually slowing the reaction down. The more hydroxide you have, the slower it gets. Mystery solved. Our secret agent wasn't helping at all. It was getting in the way. It pushes that first equilibrium step backward, which means there's less of that crucial intermediate, HOCl, available for the main event, that slow second step. It's a perfect example of just how powerful chemical kinetics can be. So why do we care about all this? I mean, this kind of chemical detective work is cool, but it's not just for solving problems in a textbook. Understanding how reactions really happen, their mechanisms, is totally fundamental to how we design and control pretty much everything around us. Yeah, I mean, by figuring out the secret plot of a reaction, scientists can basically become master controllers. They can design medicines that hit very specific pathways in the body. They can develop catalysts to make manufacturing way faster and more efficient. They can predict environmental changes or even just figure out how to keep food from spoiling. It all boils down to controlling the speed of a story that's happening on a scale we can't even see. So there you have it. A reaction that looks so simple on the page can be hiding this incredibly complex and honestly elegant story. It's just a great reminder that there's almost always more going on than what you see on the surface, which really just makes you wonder, right? What other chemical secrets are out there, just waiting to be uncovered? Thanks for tuning in.